Namaste, this is Mallikarjuna working as an assistant professor in Department of Mechanical Engineering, MIT Mysore. In the previous session of turbo machines, I hope you have gone through pi terms. We have 6 different pi terms. First one is pi 1, which is nothing but Q divided by Nd cube, where Q is the discharge, N is the speed of the turbine, D is the diameter of the rotor. This phi 1 is also called as flow coefficient because in the numerator we have the flow term, which is nothing but the discharge. Phi 2 is GH, energy per mass flow rate, N is the speed of the turbine, and D is the diameter of the rotor. This is also called as head coefficient because in the numerator we have head, and in the third pi term we have power P divided by rho n cube d to the power of 5, where P is the power, rho density, n speed, d is the diameter of the rotor, which is also called as power coefficient because in the numerator we have power. Pi 4 is mu divided by rho n d square, mu dynamic viscosity, rho density, n speed, d diameter. This is also called as viscous coefficient because in the numerator we have dynamic viscosity term. Pi 5, which is given by n square root of q divided by h to the power of 3 by 4. This is obtained by altering few of the pi terms, and it is called as the specific speed for pump. The purpose of the pump is to discharge the fluid, so that discharge term is present in the numerator, which is nothing but the q, and this is called as a specific speed for pump. And pi 6, which is nothing but n square root of p h to the power of 5 by 4, where p is the power. This is nothing but the specific speed for the given turbine. The purpose of the turbine is to generate the power, I mean conversion of the available energy into the mechanical power. So that is why this is called as a specific speed for the turbine. So these are the different pi terms which we are available with now. So by making use of these pi terms, we will be looking on to various unit quantities now. Unit quantities are the corresponding values of that of discharge, speed and power under a head of 1 meter. I mean when the device is working under a head of 1 meter, what are the values of discharge, speed and power? Those particular values are termed as unit quantities. Let us go through the different unit quantities now. First one is unit discharge, which is usually denoted by QU, and it is also called as unit flow. If you want to define the unit discharge, it is the discharge of the given turbo machine under a head of 1 meter. That means what is the discharge happening through the turbo machine under a head of 1 meter. Let us look on to the equation for the unit discharge now. We know that discharge is usually given by area times of velocity. Area, I will keep it as it is since I need to look on to the area through which the flow is happening, and velocity is given by square root of 2gh, where 2 is constant gravitational pull and h is the head with which the turbo machine is operating. In this term, 2 is constant and g is constant, h is the variable thing. If I look on to the area of the turbo machine will be dependent on the diameter of the rotor. So for a given rotor, diameter is constant. That is what I have written over here. D is constant for a given rotor. That means the area through which the flow is happening is also acting as a constant. That means constant, 2 is constant, G is constant. Only variable on which the Q is dependent on is head. So directly I have written Q is directly proportional to square root of h. Discharge or flow is directly proportional to the h, square root of h. If I eliminate the proportionality constant, I will get a constant. I have notated that constant as k into square root of h. I have called this equation as equation number 1. I have already defined a unit discharge. This is the discharge happening through the given machine under a head of 1 meter. That is what I have called as unit discharge. I am making use of that condition now. If head becomes 1 meter, then Q becomes QU. Head becomes 1 meter, then Q will become QU. That means In this equation, if I substitute the value of h as 1, then q becomes qu. That is what I have done here. Q becomes qu when h becomes 1. Therefore, I have got the value of k constant as qu. That means this constant is nothing but qu, unit discharge. I have called this as equation number 2. Now, please put this equation number 2 inside this equation number 1. That means q remains as it is, which is equal to, in this place I have k over here, k has been replaced by qu terms of square root of h. Please solve this equation for qu. Qu is equal to q divided by square root of h. Now, please look on to the definition again. Unit discharge is the discharge happening through the turbo machine when the head is 1 meter. I mean, if you divide the discharge by the head, then you will get the qu in terms of meter cube per second. So, this is what is regarding unit discharge or unit flow, which is nothing but qu. Let us move on to the second unit quantity, which is nothing but unit speed. We have already notated the speed by n. So, nu is nothing but unit speed. Now, let us look on to the term unit speed. It is the speed with which the turbo machine is running under a head of 1 meter. That means what? When head is equal to 1 meter, what is the speed with which the turbo machine is running? That is called as unit speed. We have already talked with respect to the pi term. I have pi 2 over here, gh divided by n square d square. I have taken that into consideration. Phi 2 is gh divided by n square into d square, where gh is the energy per mass flow rate of the fluid, speed with which the turbo machine is running, d diameter of the rotor. I have solved this equation for n because I am trying to define the speed. If I solve the equation for n, so this equation becomes n square, which is equal to g into h divided by pi 2 into d square. If you look onto the various term present over there, g is the gravitational pull, which is constant, pi 2 is the term constant, d diameter of the rotor. For a given turbo machine, rotor dia is constant. All these terms are acting as a constant. Now, only variable on which the speed is dependent on is h in the pi 2 term. So, n square is directly proportional to h. Here pi 2, d square as well as g are acting as a constant and h becomes the variable. N square is directly proportional to h. In the next step, I have sent square onto the other side so that it becomes the square root. N is directly proportional to square root of h. Now, if I eliminate the proportionality, n is equal to k times of square root of h, where k is the proportionality constant. I have called this equation as equation number 1. Now, I have already defined the unit speed. Unit speed is nothing but the speed with which the turbo machine is running when head is 1 meter. If h becomes 1 meter, then speed becomes unit speed. That is, if n becomes nu, then h becomes 1, or else if h becomes 1, then n becomes nu. So, nu is equal to k times of square root of 1. Square root of h becomes square root of 1. So, that this k proportionality constant becomes unit speed, which is nothing but nu. I have called this as the equation number 2, and I have substituted this equation number 2 in equation number 1. That means k has to be replaced by nu in equation number 1. I have done this over here. N is equal to k times of square root of h. K is nothing but nu times of square root of h. Now, solve the equation for nu, which is nothing but the unit speed. Unit speed is equal to n divided by square root of h. Now, again recall the definition of unit speed. It is the speed with which the turbo machine is operating under a head of 1 meter. Speed with which the turbo machine is operating under a head of 1 meter. If you divide the speed with which turbo machine is operating with the available head, then that becomes unit speed. speed with which turbo machine is happening under a head of 1 meter, and it will have a unit of RPM, regular speed unit RPM. So, that is what is regarding unit speed, which is nothing but NU. Okay. Next unit quantity is unit power. Unit power is defined as the power produced or power developed by the turbine when it is acting under a head of 1 meter. I will look on to the equation of unit power. We have the pi 3 term. Pi 3 is power divided by density, speed cube, and diameter to the power of 5, which is nothing but power coefficient. So, I have taken pi 3 into consideration, P divided by rho n cube d to the power of 5. I have solved this equation for power. Power is pi 3 times of this term, pi 3 times of that term. Now, if I look on to the terms, phi is a constant, rho density, it is an incompressible fluid, so rho is constant. So, P is directly dependent on speed and the diameter. P is proportional to the n cube and d to the power of 5. In the next stage, I have splitted this term as n square d square into n into d cube. Now, we have pi 2 with us. Pi 2 is GH divided by n square into d square. Solve the equation for GH. GH becomes pi 2 into n square d square. Solve the equation for H. If you solve the equation for H, G becomes constant, phi 2 becomes constant. So, H is directly dependent on n square and d square. In the next stage, again consider the pi 1. Pi 1 is q divided by nd cube. So, solve the equation for q. Q is phi 1 into n into d cube. Now, phi 1 is a constant. So, q is directly proportional to n into d cube. I have expressed n and d in terms of h over here. Here also n and d needs to be expressed in terms of h. That is what is my aim now. Again, I know q, discharge, is defined as area times of velocity. Q is equal to area into square root of 2gh. So, area, inside the area I will have a diameter. So, diameter for a given turbine or given rotor is constant. So, that A becomes constant, 2 constant, G gravitational force constant. So, Q is directly dependent on square root of h. I have replaced this proportionality over here. So, Q has been replaced by square root of h. So, h is dependent on n and d, or else n and d has been expressed in terms of h. Here also n and d has been expressed, n and d has been expressed in terms of h. I will substitute this two equations into the equation number 1. N square into d square has to be replaced by h. I have replaced that by h, and n into d cube has to be replaced by square root of h. I have done this. If you multiply these two things, so power becomes directly proportional to the h to the power of 3 divided by 2. If I eliminate the proportionality constant, then if I eliminate the proportionality sign, I will get the proportionality constant k and into h to the power of 3 by 2. We knew the definition. Unit power is nothing but the power produced by the turbine when the head is 1 meter. If I replace the head as 1 meter, then power becomes unit power. That means in this equation, substitute the value of h as 1 meter, so that P becomes Pu. Finally, Pu becomes K, which is nothing but the proportionality constant. I have called this as equation number 5. Substitute this equation number 5 into the equation number 4. I mean, this proportionality constant K needs to be replaced by unit power. Upon substitution, you will get P, which is equal to, in place of K, you have Pu into h to the power of 3 by 2. Solve this equation for unit power Pu, which is equal to P divided by h to the power of 3 by 2. If you again recall the definition, this is the power produced by the turbine when it is acting under a head of 1 meter. Power produced by the turbine when it is acting under a head of 1 meter, in the sense, if you divide the power by the given head, then that actually becomes the unit power, and this will also have the unit of that of actual power, which is nothing but kilowatt or megawatt, in whatever units you are going to express the power. So, this is what is unit power. Totally we have 3 unit quantities with us: unit discharge or unit flow, unit speed as well as unit power. In all these 3 unit quantities, one thing is for very sure, all these quantities are expressed when the machine is operating under a head of 1 meter. Okay, let us solve a few problems based on which we will be finding unit quantities and comparison of model and prototype kind. Let us look on to the first problem. A water turbine of specific speed 150 produces 80 kilowatt of power under a head of 15 meter with an overall efficiency 81%. Find the quantities, find the unit quantities. So now let us look onto the given data. Type is a power generating machine, in the sense the given machine is a turbine is going to produce the power, so it is a power generating machine. Specific speed 150. This we have used in the previous session, we have discussed about this in the previous session. Specific speed of a given machine is nothing but the speed of the geometrically similar machine which is working under a head of 1 meter. That is what we have termed as the specific speed. The value of specific speed is given as 150. Power produced by the turbine P 80 kilowatt, head under which the turbine is operating 15 meters. Overall efficiency of the turbine 81%. Unit quantities are the question marks to us: unit discharge, unit speed, unit power. Let us go through the unit quantities one by one. Unit discharge, which is nothing but QU. We know QU is nothing but Q divided by square root of H. In the given data, we do not have Q. We need to find the Q first. So because of that, I am making use of the formula efficiency. Efficiency is equal to P divided by rho Q GH. Solve this equation for the Q, which is nothing but discharge, P divided by N rho GH. Substitute the values. We have the power value, efficiency value, rho for the water is known since it is a water turbine, G gravitational force, head under which the turbine operated is known to us. Upon substitution, we will get the discharge value as 0.673 meter cube per second, which is essential to find the value of unit discharge. Substitute the value of Q that we have found over here in this equation and under a head of 15 meter. This is going to give us the value of unit discharge as 0.173 meter cube per second. One of the unknown is over. Second unknown, I will take it as a unit power PU. Unit power is given by P divided by H to the power of 3 by 2, where P is the power produced by the turbine, H is the head under which the turbine is operating. This is 80 kilowatt as per the data, and head under which the turbine is operating is 15 meter. Upon substitution, I will get the value as 1.377 kilowatt. In the sense, if you look onto the unit power, then per unit height, per meter height, this turbine is going to produce a power of 1.377 kilowatt. That is what is unit power to us. Second unknown is over now, that is nothing but PU. And lastly, I need to look on to the unit speed, which is nothing but NU. Equation for NU is N divided by square root of H. N is the speed with which the rotor is running. H is the head under which the turbine is operating. We do not have the value of N again, but instead of N, we have the value of specific speed. Since this is a power producing machine, for power producing machine, we have a specific speed over here, N into square root of P divided by H to the power of 5 by 4. I have made use of that equation over here, and I have solved this equation for the N because unit speed demands N, actual N. Upon solving this, I have got the value of N, speed with which the rotor is running as 495.06 RPM. Please substitute this value into this equation. 495.06 divided by square root of H, square root of 15. This is going to give us the value of NU, which is nothing but unit speed, 127.8 RPM. This means the speed of the machine under a head of 1 meter. NU is this much. PU, power produced by the machine under a head of 1 meter, will be this much, and QU, discharge happening through the device under a head of 1 meter, will be 0.173 meter cube per second. so that we have found all the 3 unit quantities. Okay, let us look on to the second problem in which we will be comparing geometrical similar machines data, and one of the unknown will be calculated. Before moving on to the problem, let us look on to the geometrical similar machines. One will be considered as model and the another one will be considered as the prototype. Prototype in the sense the actual machine, in the sense to the actual dimension, and this will be in the working condition. Model in the sense this is actually geometrically similar machine to that of the prototype, but may not be to the actual size or actual dimension, and which may or may not be in working condition. That means this is the machine which is in the working condition as per the true dimensions. This is the reduced dimension geometrical similar machine. And here one of the term will play a very important role, which is nothing but specific speed. If I am looking on to the power producing machine, then I will be looking on to specific speed of a turbine. If I am looking on to power absorbing machine, then I will be looking on to specific speed of a pump. Let us look on to the question now. A model of turbine 0.8 meter diameter. This is the model, runs at 400 RPM under a head of 6.5 meter. I have noted down all the model's data. Diameter of model is this, speed is this, and head is this much. What should be the diameter of the prototype? Prototype diameter is question mark of a specific speed 185. Prototype's specific speed is 185. That has to produce 6500 kilowatt. Prototype has to produce 6500 kilowatt under a head of 22 meters. Prototype is acting under a head of 22 meters. Assume efficiencies of model and prototype are same. Both the machines are having the same efficiencies. So now we have geometrical similar machines with us. We have various data for model as well as the prototype, and one of the data is unknown to us that has to be calculated. One of the new data what we have got here is specific speed. Specific speed of the turbine is nothing but the speed of the geometrically similar turbine which is operating under a head of 1 meter. So that is what is the specific speed term indicates to us. Now let us look on to the prototype data. We have specific speed equation with us. This is the specific speed for the power producing machine. I have taken that equation into consideration. We do not know the speed of the prototype. So I have solved this equation for the actual speed. We are aware of ns of prototype, h with which the prototype is operating, p produced by the prototype. All the values are known to us. Upon substitution, I will get n, speed with which the prototype is running, as 109.33 RPM. So I am aware of speed of the prototype now. Next we have head coefficient, which is nothing but the pi 2. Pi 2 is gh divided by n square into d square. I have taken that into consideration, and since I am dealing with the geometrically similar machine, the pi 2 remains constant for both the geometrical similar machine. On one side I will write pi 2 for model, on the other side I will write the pi 2 for prototype, and both the values are equal to us. So now g is constant because it will not vary for different kind of machines. It is a constant to us, so g will be eliminated. Now this entire term is for m, I mean model. This entire term is for prototype, I mean p. Now in this equation we are not aware of diameter of the prototype. That is what is the question mark to us. We are aware of head with which the model is operating, speed with which the model is running, diameter of the model is known, h with which the prototype is running, speed with which the prototype is running is known, dp, I mean diameter of the prototype, is not known. If you substitute all the values which are available to us into this equation, we will get the diameter of the prototype, which is nothing but 5.38 meters. So this is what is the unknown to us, which is nothing but diameter of the prototype. The value for diameter is 5.38 meters. In this we need to look on to the specific speed. Specific speed is the speed with which the geometrical similar machine is running and which produces the 1 kilowatt of power under a head of 1 meters. That is what is the specific speed. This will be taken into consideration while comparing the model as well as the prototype.